Okay, good morning students. Today we will discuss the interrupt process in 8085 microprocessor. So in 8085 microprocessor, the interrupt process only starts when interrupt enable flip-flop is high and interrupt device sends a INTR signal to the microprocessor. Okay, so that means what is interrupt actually? Interrupt is a signal that is coming from an external peripheral device. Okay, so if you want to know about the interrupt process, then first of all you need to think about that this what is going on before this interrupt process. What is actually going on before this interrupt process? This scenario you need to think first. So there are two things you need to observe. There are two things you need to observe. First of all, you observe what is going on inside the microprocessor and what is going on outside the microprocessor. Okay. So let me start with the inside the microprocessor. Say in the inside the microprocessor, say your microprocessor is busy to execute any program or busy on its own work. Okay, so this is the inside condition. Microprocessor is busy with its execution program. Okay, say some other program in this microprocessor is executing. In this, this is the current state of your microprocessor. Okay, this is the internal state of your microprocessor. And in the external side, what you have a device. You have an external device which wants to communicate with your microprocessor. That is the external side. Okay, an external device wants to communicate with your microprocessor. Okay, so that device does not know what is going on inside the microprocessor, right? That external device does not know what is going on inside the microprocessor. So you have already connected that external device with the microprocessor, and in that through that connecting pin, this external device wants to communicate with the microprocessor. Okay, so this is actually the scenario before interrupt process. There is microprocessor, there is a one external device. They are both connected through some pins, hardware pins, and microprocessor internally is busy to execute any program, and that external device wants to communicate with microprocessor. Okay, so what that external device will do then? There are other ways, but this is one of the way by which external device can take the attention of your microprocessor, right? So first of all, that external device do something by which microprocessor gives its attention to that external device, not the process that microprocessor is executing. Okay, so that is the thing interrupt process actually. Interrupt process is nothing but taking that attention of your microprocessor. Okay, how that thing is happened internally. Okay, that thing we will discuss now. So first statement that I have already read out for you. Again, I am reading that 8085 microprocessor process interrupt only when interrupt enable flip flop is high and interrupt device sends a INTR signal, that is interrupt request signal. Okay, so these two are the basic condition that needs to be fulfilled to get the attention of your microprocessor. Okay, so that means external device wants to get attention of your microprocessor. So to get that attention, two things need to be satisfied. One is that external device, that is the interrupting device. Here it is written that external interrupting device should send a signal INTR to the microprocessor. That is the first condition. That is the external signal that comes from that external device to microprocessor. And there is an internal flip flop inside the microprocessor. That flip flop name is interrupt enable flip flop. Okay, so that flip flop should be at high state, means enable state. That flip flop should be at its high state. Then only microprocessor will give its attention to that external interrupting device. Okay, so this is the very primary thing that you need to understand, that to start a interrupt process, that external device needs to send this INTR signal, as well as internally EI flip flop is at high state. Okay, so external device that is which is sending that INTR signal, that device does not have the control over that interrupt enable flip flop. Does it? Does that device is having any control? No, that is a simply external device. So actually, you are the programmer. You are writing the program. Okay, you are writing the program in such a way that whenever there is an interrupt request is coming, at that time through your program you have to make that flip flop high. Okay, so that microprocessor will give the attention to that external device, because what microprocessor is currently doing internally, it is executing some written program that is of important, as well as when that external device sends a signal to the microprocessor, this INTR signal, to do some specific work, that is also important. So both are the important tasks to the microprocessor. So microprocessor cannot avoid any of these two. But how to microprocessor manage these two important tasks is the our aim to understand here. Okay, so you know that you are the programmer, so you have to make that flip flop high. So how you make that flip flop high? You need to use some instruction. That's why here this instruction is used, EI instruction. Okay, so you need to use this instruction, EI instruction, to make that flip flop high. Okay, so if you make that flip flop high, then then microprocessor, when microprocessor gets that signal, INTR signal from that interrupting device, microprocessor will give its attention to that external device. Okay, but suppose you have not made that flip flop high, then what happens? Suppose the flip flop status is not high, but in interrupting device sends the signal INTR to microprocessor. Then microprocessor does not give its attention to that external device because the flip flop status is not high. So you can make this flip flop status high or low through your program using two instruction, EI and DI. Okay, these are very important instructions and only used for interrupting process. Okay, EI is used to enable that flip flop and DI is used to disable that flip flop. Okay, so that is the thing you need to understand. Both are one byte instructions. Okay, it is both are used for enabling or disabling that flip flop process. Okay. Okay, so the next is how. So that is, now it is clear that the flip flop status is high. Okay, the flip flop status is high, and INTR signal is received by the processor. Okay, so processor now processor is giving its attention to that external device. So now you just think little bit. If the processor gives its attention to the external device, then what happened to the internal process that is going on? Abruptly, whether that internal process abruptly stop, that is not actually our aim. Okay, that should not be do this way. Microprocessor should not do this way. Microprocessor should not abruptly stop that internal process. Okay, that is also an important task to the microprocessor. So how microprocessor will manage this? How microprocessor will manage these two important tasks? So that is written here. When microprocessor receives that interrupt request signal, then microprocessor completes the current instruction. Okay. So current instruction means whatever the instruction microprocessor is executing, it completes that execution process. Then microprocessor store the next address of the instruction into the stack. It is written within star. Okay, so because why it is storing that next address of the instruction into the stack, because once the operation of that interrupting device is complete, then microprocessor should come back to the original program, original internal program, right? So there are two programs. When microprocessor starts communicating with that external device, then there is some program need to be executed for the external device, and previously microprocessor is doing some execution. So previous program where microprocessor just stopped. So after completing the instruction, after completing the program of that interrupting device, microprocessor needs to come back to the previous program. So for that reason, microprocessor is storing the address of the next instruction into the stack. Okay. So this is the one task of microprocessor, and then microprocessor will send the interrupt acknowledgement, the signal to that interrupting device. This is the next task. Microprocessor will send interrupt acknowledgement signal with that to that interrupting device, because after getting the INTR signal, microprocessor does it is not like that. After getting the INTR signal, microprocessor is not just ready, becomes ready. Okay, means that there is some tasks microprocessor needs to do. After completing those tasks, microprocessor will send that acknowledgement signal. Okay, so some time is required for microprocessor to get ready to communicate with that peripheral device. After that particular time, microprocessor send that acknowledgement signal INTA prime. Okay, complement of INTA prime. Okay, so this signal will send to the at peripheral device. Okay, so these are the tasks, or you can say these are this is the way how microprocessor is managing two important tasks. Okay, so microprocessor basically suspend, not in totally terminate the current program. Okay, so microprocessor basically suspend the current program for some time. Okay, and then it will go to the interrupting device request. Okay, and there microprocessor will execute some program, then microprocessor come back to the suspended program and execute that program too, right? So so this is the way microprocessor handle the interrupt process. Okay, then the program sequence. So now once the program, so the term that I am using here, that interrupting device program, is also known as interrupt service routine. Okay, ISR. Okay, so what is ISR, interrupt service routine? It is nothing but a specific written small program that is that needs to be executed whenever there is an interrupt request come. So the program sequence transferred to the location of ISR of that interrupt. Okay, so 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 suppose that there are different kind of interrupt for a particular say for a particular interrupt there is a particular ISR routine need to be executed. For another interrupt, another ISR routine needs to be executed. This way, microprocessor will execute different ISR routines according to the different interrupt processes. Okay. So once microprocessor suspend the current process, it will execute the ISR routine of the particular interrupt process. Okay. So that is the case. So at the end of the ISR, so what happened? So I already told you that after completing the task of your interrupting device, microprocessor will come back to the suspended work. So that is written here. After the end of the ISR program, microprocessor will return to the previously suspended program by as there is a return instruction written at the end of the ISR code. Okay, so you can find. So this is just for your information. It is written that you can find this statement, this instruction, RET instruction, return instruction, at the end of each and every ISR routine, because microprocessor needs to come back to its previously suspended process. Okay. Okay. So this is the way microprocessor actually handle the interrupt process. I hope you understand. There are two things you need to remember here. First of all, if an interrupting device wants to communicate with microprocessor, then you need to remember that it should send INTR signal, as well as internally the programmer should make your interrupt enable flip-flop value equals to high using EI instruction. Okay, and then only microprocessor gives his attention to the interrupted device. But microprocessor is currently busy with his current work, so microprocessor does not terminate that work. Microprocessor will suspend that work for some time, and when during the suspension process, microprocessor store the value of the next instruction into the stack. Okay, and then it will send a interrupt acknowledgement signal to that interrupting device. Then it will execute the program which is written in the interrupt service routine program. Okay, after execution, it will come back to its previously suspended program and execute that program. This is the way microprocessor handle the interrupt process. So this thing you need to understand. So first of all, this is the basic introduction to the interrupt process, how microprocessor handle the interrupt process. Okay, what are the basic necessary conditions you need to satisfy before starting the interrupt process. Okay, then now I will discuss different kinds of interrupt process. There are different kinds of interrupt process, starting from hardware interrupt, software interrupt. So what is hardware interrupt? I start with hardware interrupt first. Hardware interrupt means you can find those interrupt pin in 8085 chip. Means there are particular hardware pin for this interrupt, and these interrupt names are RST 7.5, RST 6.5, RST 5.5. You can see here trap and INTR. These are the hardware interrupts. Because why hardware? Because you can find a particular pin, hardware pin in 8085 chip. Okay, you remember 40 pin chip 8085. So in that, out of that 40 pin, you can find the pins with the name RST 7.5, 6.5, 5.5, trap and INTR. That is the reason it is known as hardware interrupt. And what is RST? RST means restart. Basically, RST means restart. Okay, and there are some software interrupt also. Software interrupt means there is no particular hardware pin for this software interrupt, but these interrupts are can be generated by just writing the simple code. Okay, so RST 0, 1, RST 2, RST 3, RST 4, RST 5, RST 6, RST 7. These are the instruction basically. You if you consider this in software interrupts, these are nothing but the instruction. Okay, but if you consider the hardware interrupt, these are not the instruction. You can find hex code corresponding to this interrupt software interrupts, because these are the only instruction and these are used by only programmer. There are no physically any external device wants to communicate with microprocessor. These are just a software interrupts which can be invoked in your program by the writing of specific instruction. Okay, and what it will do, it will do the same kind of work. It will do the same kind of task which is done by the hardware interrupt. It will, so a microprocessor hardware interrupt or software interrupt is a little bit different, but the internal operation is quite same. Okay, so in case of software interrupt also, it will just jump to the particular address, ISR routine, it execute, and then it will come back to its previously suspended program and execute that. So same thing, but this is the software interrupt. No hardware pins are there, no external devices are required. By just writing some instruction, you can generate this software interrupts, and all the software interrupts are actually the instructions. You can find all the software interrupts are nothing but the instruction. RST 0, 1, 2, 3, 4, 5, 6, 7, all are the instruction. Okay, so these are the software and hardware interrupts. Okay, I hope you understand. Next is priority wise. If I say priority wise, I can say there are trap. There are trap is a hardware interrupt. So this interrupt has highest priority. Okay, RST 7.5, 6.5, 5.5. These are also the interrupts, and these interrupts having the priority according to the written sequence. Okay, so trap has highest priority, then RST 7.5, next highest priority 3.5 and 5.5, and in the last fifth one is your INTR, interrupt request. That is also hardware interrupt. So why hardware interrupt I am saying? Because INTR is not actually a particular interrupt. Okay, there is no because you can see there is a basic difference between trap, RST 7.5, 6.5, 5.5 and INTR. Both are the hardware interrupts, but if microprocessor receive this kind of interrupts at trap or RST 7.5, 6.5 or 5.5, then it will go to these locations, okay, and execute some program written in that locations. But if microprocessor receive INTR, it does not go to any location. Okay, that is the difference. INTR is a hardware interrupt, but it is not connected to any ISR routine. Okay, so that is the difference between INTR and other hardware interrupts. Okay, and why I have written these addresses? Because these are the addresses of ISR, interrupt service routine, of this particular interrupt. So for if microprocessor receive a interrupt through this trap pin, this is a pin, hardware pin. If through this trap pin microprocessor receives an interrupt, then microprocessor simply go to this location. You don't need to do anything because it is already programmed in such a way. So for trap microprocessor will transfer to this particular location, and there you need to write some instruction. If it is previously written, then okay. But if you want to change it, you can change it. Okay, according to your wish, you can change it, and microprocessor will go to this location and execute those instructions, then come back to your main program. Okay, let's say RST 7.5. So this will also related with this address. Okay, 003C. And these addresses are calculated how? If you want to say, sir, how is this addresses calculated? I will show you in the next slide. Okay, here I cannot show. I will show you in the next slide. Okay, so these are the addresses, corresponding ISR addresses to this corresponding hardware interrupts. Okay, so these are also known as vector interrupts. So priority wise, I have told you, but these are also known as vector interrupt. Vector interrupt means, you know the term vector. Vector means these interrupts, for these interrupts you don't need to provide any in ISR address. Microprocessor will simply jump to this address. So for vector interrupt, microprocessor will know the address from where the interrupts are coming and their corresponding starting address of ISR. Okay, so microprocessor know everything for this vector interrupt because these are the hardware interrupts. So microprocessor understand that from which hardware pin these interrupts are coming and in which location microprocessor needs to go after getting this interrupt. Okay, so these things are already known to the microprocessor, and these interrupts are known as vector interrupt. And there is non-vector interrupt. So what can you tell me which one is non-vector interrupt? Non-vector interrupt is your INTR, because all the software interrupts are also vector interrupt. RST 0, 1, 2, 3, 4, 5, 6, 7. Whenever you can see these numbers are associated with any interrupts, those are the vector interrupts. Okay, but there is an exception, trap. So you cannot see any number is associated with this interrupt, but it is also vector interrupt. Why? It has a particular number which is hidden, that is trap associated with the number 4.5. Okay, remember 5.5, 6.5, 7.5, and trap having the number 4.5, hidden number. Okay, so this is also a vector interrupt having that hidden number 4.5. But INTR is that interrupt where there is no number is associated. So it is a non-vector hardware interrupt. Okay, it is written here. INTR is the only one non-vectored hardware interrupt. Okay. Okay. So these are the case for this interrupt process. So vector interrupt and non-vector interrupt is INTR. Okay. The highest priority interrupt is trap. Trap. Okay. Lowest priority is INTR. These priorities I am saying about only hardware interrupts. I am not saying about software interrupts. Okay, I have not considered software interrupts. Okay, so obviously the software interrupts having the lower priority than hardware interrupt. Okay, basically in the software interrupt there is no concept of priority because software interrupts are not generated externally. They are generated through the program. So when programmer is generating something, then what is the need of giving priority? So there is no priority in software interrupt. But as the external device is generating the hardware interrupts, so there needs this priority concept. And why we are actually interested in priority concept? Because suppose two external devices tries to communicate with microprocessor at the same time, then what happened? Through this trap pin and RST 7.5 pin, if two different devices wants to communicate with microprocessor, then what happens? Then obviously microprocessor will solve this for trap interrupt process, not RST 7.5, because microprocessor will see which interrupt has higher priority. Okay, if the microprocessor receives two priority, one is RST 7.5, RST 5.5. So which one will be solved first? RST 7.5. Right? If microprocessor receives the two interrupt RST 6.5 and 5.5, which one will be solved first? RST 6.5. Okay, so this way microprocessor handles this hardware interrupt process according to their priority. And in case of software interrupt, there is no need of priority because you are the programmer, you are writing the code for generating the software interrupt. So why should anyone bother about the priority in case of software interrupt? Okay, so that is the all of these things related to priority, vector interrupts, hardware and software interrupt. These are the categories of interrupt. Okay, and this diagram actually I have just drawn so that you can understand that masking process. Masking is one of the important process in interrupt process, in interrupt handling situation. Masking. What is masking? Masking means what? Masking means suppose you got microprocessor received an interrupt request from this particular pin IST 6.5. Okay, so when after receiving this request, there is a possibility. There is a possibility because you are the programmer. You have to decide. You have to decide that if you receive suppose you have written a 10 line of code. Okay, suppose you have written a 10 line of code, and during execution of 10 line of code, you don't want to solve any interrupt process. Okay, listen very carefully. Suppose you have written 10 lines of code, and when microprocessor execute that 10 lines of code, you don't want to solve any interrupt process. That whether that is the possible, whether this condition can be achieved. Yes, it is achievable. Why? Because masking operation is here. Masking means you can mask if you microprocessor receive an interrupt. Okay, microprocessor can mask that interrupt. How? There are some instruction by which you can use this masking operation. Okay, so for that reason I have shown here that there is a mask. This column is a masking column. So if you give a proper value here, then obviously you will not a proper value at this output gate. And you can see this is an AND gate. So to get 1 at the output, all of the inputs should be 1. Okay, so all of the input will be 1, but if you make something in this box so that you give 0 here, then obviously you can mask that particular interrupt. Okay, so this AND gate, what is the purpose of this AND gate? This AND gate will actually locate this vector location. Okay, so the output of this AND gate will decide whether to go this vector location or not. Okay, so this AND gate is having 3 inputs. One is the request that is coming from that hardware pin. One input is your masking bit, and another input is enable. Enable means you need to enable this gate. Okay, without enabling you cannot do anything. So this enabling this gate is done by this EI and DI instruction. You see EI and DI that I have already told you. Using EI you can you can make high the interrupt enable free flow. So using EI and or DI instruction you can enable these AND gates. Now after enabling these AND gates, suppose you have enabled these AND gates, but you don't want to solve this particular interrupt. Okay, IST 7.5. You want to mask it. So it is possible. Yes. Is it possible? Yes, it is possible because you can put 0 here. Okay. If you use this particular masking box in a particular way, then it is possible to mask that particular interrupt. Masking means you are not solving that interrupt process. Okay, so it is associated. This mask block is associated with RST 7.5, RST 6.5, RST 5.5. But this block, masking block, is not associated with track because it has the highest priority. So you cannot mask track. Okay, so this is also very important information. Which interrupts you can mask? 7.5, 6.5, 5.5. But you cannot mask track because there is no provision is given in the architecture of 8085. Okay, and how you do the masking operation? So that is now I'm going to say. So if you want to do the mask operation, okay, then you can basically you need to use this instruction SIM. Okay, using SIM instruction you can mask any of the interrupt process. Okay, any of the interrupt process means IST 7.5, 6.5, 5.5. I'm talking about only these 3. Okay, not track. Okay, so how I can use this instruction? So SIM set interrupt mask. This instruction, to understand this instruction you need to understand this 8-bit format. Okay, so in this 8-bit format, because basically a 8-bit data. Okay, so you need to give a 8-bit data in such a way that it will be used by this instruction to make some this interrupt mask or unmasked. Okay, masked or available, right? It is written masked or available. Okay, so this data frame you need to prepare first, then you need to use this instruction. Okay, so first of all you need to make an 8-bit data frame, according to some rules and regulations, then you can use this instruction to make particular interrupt, say any of these three interrupt must or available. Okay, so how, what is the rules and regulation? Rules and regulation is like that: D2, D1, D0, these three bits value you can change 0 or 1. Okay, if you make this bits value 0, then it is available. If you make it this bit value 1, then it is must. Okay, so you can see that 5.5, 6.5 and 7.5. So if you want to mark 7.5, you need to make this bit value 1. If you want to mark 6.5, make this value 1. If you want to mark 5.5 interrupt, you need to make this D0 value equals to 1. Okay, and if you want to make them available, you can make them 000. But these three bits only work when you have make this D3 bit value equals to 1. Okay, because this is the mask set enable. So this will enable D3 bits. D3 bit will enable D2, D1, D0 bits. So D3 bit should be 1. Mask is at set. If you put 0 at D3 bit, then all the bits from D0 to D2 will be ignored. Okay, there is no value of these bits D0 to D2. So basically, if you want to do the masking operation, so then you need to prepare your 8-bit data according some rules and regulations, and these are I am saying here. So you can make D2, D1, D0 according to this. You need to make D3 value equals to 1 if you want to use D2, D1, D0, and D4. D4 is used for what purpose? It is used to reset. Reset. It is not a mask. It is used to reset. Reset is different thing. Mask is different thing. Mask means what? You have masked it. Means you have not made. You have not made. You have just suspended this particular interrupt process for some time. Masking means one. You can say the suspension for some time. You can unmask them, make it available, then you can do its operation after some time. But reset means you are just making it 0. Okay. So RST 7.5 can be reset using the bit number D4. If you want to reset it, put it value equals to 1. Then the D5 is ignored. D6. Okay, D6 and D7. Okay, so D6. D6 and D7, these two bits are basically used for serial data output, SOD, serial output data. Okay, so you need to enable that. Means if you put, means basically this is not used in interrupt process, this is used in serial communication process. Okay, so I don't want to say anything about this, but you just need to know that if there are this SIM instruction, through SIM instruction you can handle the interrupt process, right? Like masking or making available, as well as you can serially send out data from microcontroller. Okay, serial output data, serially out. You can send out the data from microcontroller. Okay, this thing you need to this thing is very important that you need to understand. You can do two things using SIM instruction. You can handle interrupt process. You can handle serial output data process. It's serial communication process, serial output data process. Okay, so that is the SIM instruction, and I have shown some 2 or 3 lines code here just to make sure your concept. Okay, suppose I want to write a program by which I want to enable all the interrupts of 8085. I want to enable them. Enable means making available. Available, to make available, what you have to put? You have to put 0, D2, D1, D0 value should be 0, 0, 0, and D3 value you can put 1. Okay, so if you put 0 here, then these 3 bits will not be considered. So you need to put 1 at the D3. So D3 1 and all these 0. So it becomes 80. 8. No, sorry, it becomes 8. And other bits are not useful. So you put all 0000. So your data becomes 08, right? So that is the formation of your data 08. So first of all, you need to form this data 08. Then you start writing this code. So first of all, you need to enable the flip-flop EI because you are handling the interrupt process. So you need to enable that interrupt enable flip-flop. So by EI instruction, you make it. Then you send the data that you have calculated into the accumulator. Okay, and then use this SIM instruction. Okay, so this is the way you can use the SIM instruction. Means you have to prepare the 8-bit data. You will need to send that data into accumulator, then use SIM instruction. Okay, this is how the SIM instruction works. Okay, so I can show you that suppose I want to reset at RST 7.5 because this is the one operation that we can do using SIM. Reset RST 7.5. So to reset the RST 7.5, what you have to do? So to reset the RST 7.5, you have to make sure that which bit is for RST 7.5. This one, D4. Okay. So D4 value should be 1 to reset it. And when you are when you are resetting this, you are not going to affect any other interrupt. So you remain the 80. You remain. So you put 1 here at D4 bit, and at D3 bit you put 1 again, and all these D2, D1 and D0 bit equals to 000, because you are actually interested to only reset the RST 7.5 and you are not interested to make any changes to other interrupt processes. So that's why you are making every process as available. Okay. So that is the code for reset RST 7.5. Now, as this instruction SIM instruction is used to actually make some interrupts enable or means available or mask, there is another instruction by which we can also read the current status of different interrupts. Okay, so current status of different interrupts means suppose if you want to read what is going on inside the microprocessor related to the interrupt processes, what is going on, what is currently going on. So you can read it through the instruction RIM. Okay, RIM, read interrupt mask. Full form is read interrupt mask. Okay, and SIM full form is set interrupt mask. Okay, so SIM SIM is used to make some interrupts enable or disable, masked or unmasked. Okay, so that's why it is known as set interrupt mask, and a read is used to read the status, so it is known as read interrupt mask. Okay, here also after reading you will get an 8-bit data, and you need to understand that 8-bit data using some rules and regulations, right? You need to understand that 8-bit data after reading what you are getting using some rules and regulations. So which the rules and regulations are like this. So suppose you read the data, you get that data, say in that particular bit, in this D0 position bit, you are getting 1. Okay, so interrupt masked. If you get this bit value 1, D2, D1, D0, so this corresponding, if you get 1, 1, 1, so that means these interrupts are masked. Okay, if you get at the D3 1, that means interrupt enable flag is enabled. Okay, interrupt enable flag is enabled. So that means you are reading. Here you are actually not making any changes. You are just reading. So if you when you are reading, if you get that D0 bit equals to 0, that means the RST 5.5 is available. Okay, 0 means available. Here you can match. If you want to make RST 5.5 available, so you have to put here 0. So that thing you are actually reading here. So when you are reading, if you get here 0, that means it is available, and if you get here 1, that means it is marked. Okay, so you can easily understand there is a direct link between SIM and RIM. Whatever you are putting in SIM, you are reading through the RIM. If you put in the SIM D0 bit 0, making the RST 5.5 enable, then similarly you will get in through the RIM instruction D0 bit 0. That means RST 5.5 is enabled. If you put in through the SIM instruction, SIM instruction, if you put the value of D2, D1, D0, all these three bits equals to 111, then when you read, you will get same thing 111 value at D2, D1, D0. That means all these three interrupts are masked. Okay. If you give D3 value at using SIM instruction, if you don't give D3 value, then obviously D2, D1, D0 value will not work. Okay. But here, if you read that the status of your different interrupts and get that at the D3 value you are getting 1. So what actually this means? This means actually the internet enable flip flop is now high state. Is now at high state. It is enable state. Okay. So not only you can read the status of different interrupts RST 7.5, RST 6.5, RST 5.5. You can also read the status, current status of your interrupt enable flip flop, whether it is enabled or disabled by the reading of the bit number D3. Then you can also read whether any of the interrupt RST 7.5, 6.5 or 5.5 is pending or not. Pending means what? I have told you, when microprocessor marks a particular interrupt. So this is, I have told you the term using suspension, suspend that interrupt process for some time. So that suspension or suspended interrupt is also known as here pending interrupt. Okay, so that means if any of the interrupts is already pending, then is in pending state, then you can read that interrupt. You can read the value of that interrupt using these three pins. Okay, if you get D6 pin value equals to 1, that means RST 7.5 is pending. If you get D5 pin value 1, then RST 6.5, this particular interrupt is pending. Okay, so you can read two status, whether any of the interrupts is marked or available, that is one status, whether any of the interrupts is pending, that is the second status. You can read the status of your internal enable flip flop. Okay, these three things you can read using RIM instruction. Similar to the SIM instruction, this RIM instruction is also used for your serial communication. You can read the data. RIM means reading. So if you are doing interrupt process, you are reading the status of different interrupts. If you are doing the communication process, serial communication process, you are reading the data which is coming into the microprocessor. So it is bit number 7 is used for serial input data. Okay, reading. Okay, and SIM instruction is what it is used for giving out the data, right? So giving out the data. So remember this three also. Okay. This is a small example, like SIM instruction. Here also I have shown a small example. Suppose I'm not going to read this problem statement. I just want to give you the brief of this program. Suppose I have used RIM instruction first. How I use this RIM instruction? I told you that to read the status, you need to read the use the RIM instruction. But how? The process is here. First, use RIM instruction. So what if after reading the RIM instruction, our accumulator will be loaded with some data. Okay. So which data? The data that is loaded into the accumulator after RIM instruction execution will need to be understood. Will need to be understood by using these written rules. Okay. So you get some data into accumulator. You move that data into register B. Okay. Say after getting the data, I move the data into register B. Then I want means I don't know what data I receive in the accumulator, right? You are the programmer, you have used the RIM instruction, you don't know what you get in the accumulator after execution. Okay, suppose you get something, okay, because it is not actually when you execute your program in real life, not in the simulator. In real life, when you are executing any program, and so you cannot go again and again go and simulate your program step by step and check what is there in accumulator, what is there in this register, what is there in other register, like this. Okay, so when you just think about the real time application. So when you are applied, you have written everything, every program code, everything, and you have applied this thing in a real time application. Then you cannot go for cross checking your program step by step. There, suppose after reading the instruction status by ream instruction, what you get in the accumulator, you want, if you want to cross check that what I have received. Okay, how you can cross check? You have to use the AND operation. AND operation means why? Because suppose you want to check what is the value I am getting after reading at the bit number 0. How you can check? You don't need to check other bits. So you can add other bits with 0 and add this D0 bit with 1. If you get 0 value after AND operation, then you can understand that you have received 0 at this particular pin. And if you get non-zero value, that is 1 after the AND operation, then you understand that the value of this particular pin is 1. Okay, so that is the way you can get the information of the status of particular bit after reading the instruction. So only reading the instruction will not serve your purpose. Only RIM instruction will just read the instruction and get the data into the accumulator. Then you have to use this AND operation to understand that what is the status of any particular pin. So like that here I have used ANI 20. So what actually I am checking here? 20 means what? 0 0 1 0. So that means I am checking this particular pin, fifth pin. Okay, 20 means I am just making other pin. I am just ANDing other pin value with 0, and I am only ANDing the pin value 5 with 1, so that I can check what is whether the RST 6.5 interrupt is pending or not. Okay, so that is the purpose. So ANI 20, it will check whether RST 6.5 interrupt is pending or not. So if I want to check whether RST 6.5 is marked or not, then what I have to do? I have to AND with 0 2. Here I have AND with 20. There I have to add 0 2. Okay, and with 0 2. So then I can check whether the RST 6.5 is marked or not. Okay, I hope you understand. So that is the thing you can do using these two instructions, read and see. If you want to use SIM instruction, first of all you have to give the data, you have to prepare the 8-bit data according to the written rules. Okay, and you send that data into accumulator and then use SIM instruction. Okay, but if you want to use RIM instruction, simply you can use RIM instruction, get the data into accumulator, and then you can directly use the AND operation to check the status of any particular pin according to these rules. Okay, you need to understand this rule first, otherwise you cannot decide by which data you will going to do the AND operation. Okay, so this is the thing related to interrupt process, and these are the information that you need to understand. But I have not shown you. I have not clearly shown you what is the exact application of the interrupt process. For that purpose, I have to go with some other topic. That is, this topic is peripheral device communication. This what external device is peripheral device. So when we are connecting any external device with microprocessor and wants to communicate between them, then there we have basically 3 processes. We have synchronous peripheral device communication process, asynchronous, and interrupt driven. So you can see the third one, this interrupt driven communication process, it is totally depends upon the interrupt process. So that is the application of interrupt process. That, like I said, I have told you different things, but this is the exactly way you can understand that interrupt driven peripheral communication process is there, by which you can do the peripheral communication with microprocessor. Okay, efficient. It is the third one. It is the most efficient process. It has the advantage over asynchronous and synchronous. Okay, we'll discuss this thing when we discuss this peripheral device communication. But here just you can see that where we can apply this interrupt concept. We can apply this interrupt concept when we are communicating any external devices. Okay, and this has the highest good advantage over other processes, asynchronous and synchronous. Okay, so this is the thing that you need to understand for this particular interrupt process. Okay, and here in this question answer set, I have written some questions related to this discussion that we have done till now. There you can see that all the questions I have written, okay, for your clearance, basic clearance, or you can say for revision. And one thing that I have not shown you how we can calculate this vector address. So I am going to show you here. Suppose for RST2 you want to calculate the vector address. Okay. So for that purpose, what you have to do, you have to multiply 2. You have to consider 2 as a decimal number. Multiply with another decimal number 8. So you will get a decimal number 16. Then convert this decimal number into hexadecimal. So you will get 0010, right? This will give you 0010. Sorry, this will give you only 10. Okay, and you know that address should be 16 bit, so you put 2 previous 0, so you will get 0010. Okay, suppose if you want to calculate RST1 inter address, so 1 is there, so 1 into 8, so you are getting 08. So 08 is the decimal number. So if you want to convert it into hexadecimal, you will get 08 again. Okay, so 08, and you need to put 2 before 20 before 08. So 0008 is the address of your vector address of your RST1. Okay, so 3 into 8, 24. This is a decimal number. Convert it into hexadecimal, you will get 18. Okay, so 0018 is the vector address of RST3. Like that, in this case also you can see. Okay, RST 7.5, 7.5 into 8, that is 60 in decimal. Convert it into hexadecimal, you will get 3C. So 003C is the vector address. And trap, I have already told you, it is the 4.5. Hidden number is what? 4.5. So you do 4.5 into 8 and convert it into hexadecimal, you will get 20. Okay, so I hope this is clear. Okay. So I thank you.